Let us now understand the equivalent circuits of transformer as follows. No load equivalent circuit. Equivalent circuit parameters referred to primary and secondary sides. Approximate equivalent circuit. Click each to know more. Here is the no-load equivalent circuit of transformer. No-load current I/O is 3 to 5% of full load current. And here are some other parameters. The effect of circuit parameters shouldn't be changed while transferring the parameters from one side to another side. It can be proved that a resistance of R2 in secondary is equivalent to R2 upon K square will be denoted as R2 dash, that is, equivalent secondary resistance with respect to primary, which would have caused the same loss as R2 in secondary. While transferring secondary parameters to primary side, this is how the circuit and parameters change. Similarly, while transferring primary parameters to secondary side, this is how the circuit and parameters change. Click here to see equivalent circuit with respect to primary with all parameters. Since the no-load current is 3 to 5% of the full load current, the no-load circuit can be neglected. Transformers can be classified into the following categories based on their application. 1. Distribution transformer. 2. Power transformer. 3. Current transformer. 4. Potential transformer. 5. Furnace transformer. 6. Booster transformer. 7. Rectifier transformer. 8. Locomotive transformer. 9. Mining transformer. 10. Phase shifting transformer. 11. Welding transformer. 12. High voltage testing or SC testing TRF. 13. Grounding transformers. 14. Converter transformer. Here we have the major factors that affect the selection and sizing of transformers. Transformation from which voltage to which voltage, example 11 kV to 6.6 kV. Power requirement to be met presently and in foreseeable future in terms of kVA, MVA, connected load, demand factor and diversity factor. Power factor of load to calculate the kVA, MVA rating of transformer. Harmonic content of loads to be supplied. Transformer needs to be derated for harmonic loads, K factor. Any need for supply of high currents for short duration. Unbalance in phase currents of loads. Transformers supplying single-phase loads tend to have more phase unbalance in load currents. Configuration of windings. Delta, star. Based on need for neutral, filtering of third harmonic currents, tertiary winding for auxiliary supply, etc. Need for paralleling of transformers. Parallel operated transformers have to meet certain criteria such as same primary and secondary voltages, percentage impedances within a band, etc. Need for voltage adjustment. On-line or off-line tap changer. Voltage regulation and efficiency that is required. Indoor or outdoor application. Ambient temperature. Type of cooling. ONAN, ONAF, etc. Insulation medium. Oil, Epoxy dry type. Dry type is a maintenance-free, does not pose fire hazards, spill hazards. Type of neutral earthing. Solid, resistance, reactance, tuned resistance based on magnitude of earth fault currents, suppression of transient voltages, system insulation, etc. Percentage impedance from the point of reducing fault levels. Higher percentage impedance reduces fault levels. Level of protections based on criticality of transformer. Mounting, pole mounting, plinth mounting. Level of pollution in the environment. Bushing design and selection depends on pollution level. Altitude of installation. Installation at above 1000 meters would need D-rating of equipment. Voltage level selection is done based on the current and load requirement. The voltage level is categorized as 480 volts, 2400 volt, 4160 volt, and so on for better selection based on the requirement.
Click each tab for more information.
Next, let's look at some important terms that affect the voltage level selection. Load forecasting, demand factor, and diversity factor. Click each tab for more information. Load forecasting is a technique used by power or energy providing companies to predict the power or energy needed to meet the demand and supply equilibrium. The accuracy of forecasting is of great significance for the operational and managerial loading of a utility company. Demand factor is the ratio of the sum of the maximum demand of a system or part of a system to the total connected load on the system or part of the system under consideration. Demand factor is always less than 1. Diversity factor is the ratio of the sum of the individual maximum demands of the various subdivisions of a system or part of a system to the maximum demand of the whole system or part of the system under consideration. Diversity is usually more than 1. Now, since you know the formulas, let me ask you a question. Do the calculations and enter your answers. So, let's begin with our next topic. Testing of transformer is carried out as per IS 2026. Transformer testing is done in 3 ways. 1. Routine tests. 2. Type tests. 3. Special tests. Click each tab for more information. Routine tests are carried out on each job and can be classified as follows. 1. Measurement of winding resistance. 2. Measurement of insulation resistance. 3. Separate source voltage withstand test. High voltage tests on HV and LV. 4. Induced over voltage withstand test. DVDF test. 5. Measurement of voltage ratio. 6. Measurement of no load loss and current. 7. Measurement of load loss and impedance, efficiency and regulation. 8. Vector group verification. 9. Oil BDV test. Click each tab for more information. This test measures the resistance of the HV and LV winding. The values of resistance should be balanced for all three phases and should match the designed values. Equipment used is digital resistance meter. Measures the insulation resistance of HV and LV windings with respect to earth body and between LV and HV winding. Insulation tester or megger is used. Recommended values are 2000 m-ohms for HV and 500 m-ohms for LV. This test checks the insulation property between primary to earth, secondary to earth, and between primary and secondary. HV high voltage test. LV winding connected together and earthed. HV winding connected together and given 28 kV for 11 kV transformer for 1 minute. LV high voltage test. HV winding connected together and earthed. LV winding connected together and given 3 kV for 1 minute. Equipment used is high voltage tester, 100 kV and 3 kV. This test checks the inter-turn insulation. For a 11 kV upon 433V transformer, 866 volts are applied at the 433V winding with the help of a generator for 1 minute. This induces 22 kV on 11 kV side. The frequency of the 866V supply is also increased to 100 Hz. Equipment used is motor generator set. This test measures the voltage ratio as per the customer's requirement. The voltage ratio is equal to the turns ratio in a transformer. V1 upon V2 equals to N1 upon N2. Using this principle, the turns ratio is measured with the help of a turns ratio meter. If it is correct, then the voltage ratio is assumed to be correct. Equipment used here is turns ratio meter. The iron losses and no load current are measured in the test. The 433V winding is charged at 433V supply and the 11 kV winding is left open. The power consumed by the transformer at no load is the no load loss in the transformer. Effect of actual frequency must be taken into account. Equipment used are watt meters or power analyzer. This test measures the power consumed by the transformer when the 433V winding is short-circuited and the rated current is passed through the 11 kV winding. This test verifies the DYN11 vector group of a distribution transformer. Here, vector group means angular displacement between HV and LV of same phasor. For example, capital R and small r. Equipment used here is voltmeter. Oil breakdown voltage is checked as per IS-335. This includes 100 mm length into 70 mm breadth into 80 mm height glass pot, 500 ml oil sample, spherical electrodes with gap of 2.5 mm, Recommended value is 60 kV. Type tests are carried out only on one transformer of the lot. They are done to check the design and process parameters. They include all routine tests. Additionally, following tests are included in type tests. 1. Lightning impulse test. 2. Temperature rise test. Lightning impulse test. All the dielectric tests check the insulation level of the job. Impulse generator is used to produce the specified voltage impulse wave of 1.2 upon 50 microseconds wave. One impulse of a reduced voltage between 50 to 75% of the full test voltage and subsequent 3 impulses at full voltage. For a 3-phase transformer, impulse is carried out on all 3 phases in succession. The voltage is applied on each of the line terminal in succession, keeping the other terminals earthed. The current and voltage wave shapes are recorded on the oscilloscope, and any distortion in the wave shape is the criteria for failure. Special tests can be categorized as follows: additional impulse test, short circuit test, measurement of zero-phase sequence impedance test, measurement of acoustic noise level, measurement of harmonics of the no-load current, magnetic balance test. Short circuit withstand ability test. This test measures the ability of the transformer to withstand the mechanical and thermal stresses caused by the external short circuit. HV terminals are connected to the supply bus of the testing plant. The LV is short-circuited. The testing plant parameters are such adjusted to give the rated short-circuit current. Supply is made on and closed after specified duration of short circuit. The record of current waveform is noted. There should not be any mechanical distortion, fire to the transformer during this test. Similarly, no waveform distortion. The transformer should also withstand the routine tests after the short circuit test. The reactance of the winding measured before and after the SC test should not vary beyond the limits stated in the IS 2026. Transformer is the heart of any power system. Hence, preventive maintenance is always cost-effective and time-saving. Any failure to the transformer can extremely affect the whole functioning of the organization. The maintenance procedure for any transformer includes the following guidelines. First screen. Oil. 1. Oil level checking must be done and leakages must be attended. 2. Oil BDV and acidity checking should be done at regular intervals. If acidity is between 0.5 to 1 mg/kOH, oil should be kept under observation. 3. BDV, color and smell of oil are indicative. 4. Sludge, dust, dirt, moisture can be removed by filtration. 5. Oil when topped up shall be of the same make. It may lead to sludge formation and acidic contents. 6. Insulation resistance of the transformer should be checked once in 6 months. 7. Megger values along with oil values indicate the condition of transformer. 8. Periodic dissolved gas analysis can be carried out. Bushings. 1. Bushings should be cleaned and inspected for any cracks. 2. Dust and dirt deposition, salt or chemical deposition, cement or acid fumes depositions should be carefully noted and rectified. Breather. Periodic checking of any loose connections of the terminations of HV and LV side must be done. Breather examination or dehydration of silica gel must be done if necessary. Explosion vent. Explosion vent diaphragm examination is also important. Conservator. Conservator must be cleaned from the inside after every 3 years. OTI and WTI. Regular inspection of oil and winding temperature meter readings must be done. Cleanliness in the substation yard must be done with all nets, vines, shrubs removed. The best way of protecting a transformer is to have good preventive maintenance schedule. The maintenance schedule includes taking care of oil temperature indicators, winding temperature indicators, because relay, magnetic oil level gauge, explosion vent, HT fuse and DO fuse, LT circuit breaker, HT circuit breaker with overload, earth fault relay tripping, oil surge relay for OLTC, PRV for OLTC, horn gaps and lightning arrestor, breather. Now that we know the measures for protecting the transformers, let's take a look at the failures that can take place in a transformer. Insufficient oil level, seepage of water in oil, prolonged overloading, single-phase loading, unbalanced loading, faulty termination, improper sized lugs, etc. Power theft, prolonged short circuit, faulty operation of tap changer switch, lack of installation checks, faulty design, poor workmanship, improper formation of core, improper core bolt insulation, burr to the lamination blades, improper brazing of joints, burr or sharp edges to the winding conductor, incomplete drying, bad insulation covering, insufficient cooling ducts in the winding, bad quality of raw material, transit damaged transformers. After failure, transformer is removed and replaced with new or repaired one without removing the cause of failure, which results in immediate or short time failure. Let us now look at the causes of these failures. Environment, system, maloperation, wrong design, manufacture, material, maintenance. The transformer failures can be classified as external failures and internal failures. They are as follows. Internal failure causes winding and terminal faults, core faults, on-load tap changer faults, overheating faults. External failure causes abnormal operation condition, sustained or unclear faults. Let's look at the fault current distribution. Let's first understand earth fault on transformer winding.
Click the zoom icon to view the diagram.
The basic protection of transformers can be done in 4 different ways. Differential, restricted earth fault, overfluxing, overcurrent and earth fault. Let's deep dive into 3 main types of protection. Differential protection, restricted earth fault protection, combined differential and restricted earth fault protection. Click each to know more. Click each to know more. Differential protection works on the principle of Moore's price current comparison. In this case, only relays with bias characteristics should be used. It is only applied where protection coordination is difficult or not possible using time-delayed elements. For fast fault clearance. For zone of protection. There are several considerations for applying differential protection. These include phase correction, filtering of zero sequence currents, ratio correction, magnetizing inrush during energization, overfluxing. The principle behind differential protection can be explained with the help of following circuit diagram, having an incoming feeder and an outgoing feeder. Click each image to view the enlarged version. Biased differential protection is preferred due to its fast operation, adjustable characteristic, high through-fault stability, CT ratio compensation, magnetizing inrush restraint, overfluxing fifth harmonic restraint. So, let's understand why this bias characteristic. Click each image to view the enlarged version. Click each to know more. Restricted earth fault protection uses the high impedance principle. It has increased sensitivity for earth faults, REF elements for each transformer winding, CTs which may be shared with differential element. In REF, under normal conditions, the stability level is usually maximum through fault level of transformer. So, under normal conditions, no current flows through the relay, which means no operation. Let's understand the diagram in detail. On HV side, residual current of 3 line CTs is balanced against output current of CT in neutral conductor. For LV side, ground faults occurring on delta winding may also result in fault current of less than full load. HV overcurrent relays cannot provide adequate protection. Relay connected to monitor residual current will provide restricted ground fault protection since delta winding cannot supply zero sequence current to the system. Both windings can thus be protected separately with restricted ground fault protection. This provides high-speed protection against ground faults over whole of transformer windings. Here, the relay used is instantaneous high impedance type. It is very much possible to combine both differential and restricted ground fault protections onto one set of line CTs, or in other words, by using interposing auxiliary CTs. This in turn saves expenses of providing separate cores for each protection systems. Congratulations! You have successfully completed this training module on transformers. Now that you have completed this module, you will be able to define transformer and its working principle, explain construction of core and shell type transformers, draw phasor diagrams of working of transformer, make an equivalent circuit of transformer, list different types of transformer as per applications, execute tests and maintenance of transformer, and protect transformer from different faults.